All right. So how did these go?
They're interesting.
It was fun trying to optimize them, but I think that we found a pretty good pathway.
Yeah, so one of the things you can look at is, again, the fact that we're ending with an aldehyde here tells us ozonolysis, right? And we can start with the same starting material and go two different routes with it to create two different. So since we're trying to make something with 1, 2, 3, 4, 5, 6, with 6 carbons, it might be an advantage to actually take this molecule and add it to itself. Take this molecule and turn half of the molecules into an alkanide that acts as a nucleophile, and take the other half of the molecule and turn them into a bromide. So you can take that approach too, since I said stick to ethyl iodide or methyl iodide. The other option is to use this molecule twice as a starting material. So because if you add it to itself, you could get 8 carbons, right? And then you could cut that down to 6. So again, this is another case of there's more than one option, for sure. If you just take it the way that we've been doing it, then if you're limited. And so the fact that we're trying to get to 6 carbons, including an aldehyde, tells you that there's got to be an ozonolysis in there at some point, right? So we could get to 8 carbons potentially, and then put it through ozonolysis by putting the pi bond in the right spot, cut off those other 2 pieces. Might be a particularly good way to do that. Let me pull up the Klein textbook.
I did it a different way than ozonolysis.
Yeah.
Okay.
He came up with just the hydroboration, right?
Yeah.
Oh yeah, you
Just
can do the
turn-
hydroboration. Yeah.
Terminal alkyne and then just hydroboration.
So then if you use
Then
a
that would leave the
acetylene,
aldehyde.
that actually is probably the better option.
That was the first one. We came up
Yeah.
with.
Yeah.
Because if you
can't
use
sweat steps.
acetylene as your carbon source, you can add 2 carbons that way, right?
Yeah.
So that, and then you can
Walk the pi bond down and then.
right. So turn this to 1 bromo, so do an anti-Markov addition to be 1 bromobutane. So that's gonna be the target for acetylide, then start with acetylene, expose it to sodium amide, deprotonate it. Then you can add 2 carbons that way, and you've got a terminal alkyne still. And then doing the hydroboration. That's the best way to do it. Good call. And that was my first thought too, because I didn't think about using hydroboration to make an aldehyde. My first thought was ozonolysis to make an aldehyde.
That's what I was thinking too.
If
If we bend the rules a little bit, if we just use iodopentane.
If you use iodo,
Then, yeah, it makes it. But
so and a lot of so what if it's not specifically iodomethane or ethane, then you can start from pentane.
yeah.
But then you have to brominate it,
Right.
set it up the right way to make it 1 iodo pentane. That works too. That's one of the things I mean by you can have 2 synthesis going in parallel and then combine them at the end. So sometimes making the right bromide so that you can do an acetylide addition is actually the tricky part.
Doing adding the settlement platform, that's the way to do this.
What did it say on the notes? What page? I just had it pulled up here. But, where's my PowerPoint? There it goes.
Sorry.
493, 494. So here's the book answer is exactly what you described. You turn this into target for acetylene, add 2 carbons, and then do the hydroboration, to make an aldehyde out of it.
I got real lucky turning to that page in my notes. I was just like.
All right, and the second one, we're just trying to add
Yeah.
1 carbon. So this would be a good case for using methyl iodide. So here's our option down here. If we start by turning this into a terminal alkyne, and then deprotonate it and add methyl iodide, we get this, which then we can do the dissolving metal reaction to get the trans. Right, if we wanted the cis, we would use the Lindlar's catalyst. And this does also have, so we do have to go, since we can't make an alkyne right there, we have to do an addition to add bromine, elimination here, and then dibrominate and use the double to do the double elimination. So your final synthesis pathway is 8 steps long, because several of those are those 2-step reactions. So anti-Markov-Makov addition to put a bromine right here. Elimination, dibrominate, deprotonate. That's just to neutralize the excess ammonia. I guess you could combine these.
So why would you do 5?
You wouldn't do 5, yeah, you wouldn't do 5 and 6 if you're using excess sodium amide. I guess maybe so you could get a stoichiometric amount of the sodium.
Would that matter?
Amide, it shouldn't matter. So you could combine those. I would probably combine those. 4, 5, and 6, just make that all 1 step, excess sodium amide. And then methyl iodide is your target, then your dissolving metal reaction.
The adding acetylene, that's a good put in the toolbox.
Yeah, and we almost always have acetylene as one of our precursors. When I was talking about adding extra carbons, and I said just methyl iodide or ethyl iodide, other alkanes and acetylene are also good sources of carbon that are pretty much always available.
Because with A, what I did, I was trying to figure out how to like minimize steps, because I added the ethyl iodide, and then you have this alkyne in the middle of your molecule. So I was like, just knock it out with hydrogen and platinum, turn that into an alkane, and then from there do a monochlorination to get like enough of the 1-chloro, and then go from there. But that's like the yield on that.
Right.
Yeah.
So that's technically a valid answer.
Yeah.
I don't know on a test how I would grade that. It would be most of the credit.
Yeah.
Probably a 9 out of 10.
Yeah.
Because yes, that is a valid synthesis pathway. It's far from the best one though.
Yeah. You really want the chlorine to work, don't you?
So any other questions on these synthesis? And like I said, Thursday is going to be a bunch more practice with these. So that's also more practice with the reactions, right? But we really want to get down Markov-Makov versus anti, Zaitsev versus Hoffman. And then the rest of it is sort of, extra on the outside, the accoutrement, to sort of go along with it. Those are our biggest tools, our addition and elimination reactions. All right, this poor 6-year-old laptop, for some reason, it really struggles when it's not plugged into the power cord to also connect to a projector. But since this is a relatively short one, so these slides are some review with of NMR, proton NMR and IR. That we can go through, but the main thing, since sometimes in the past I've used these slides in OChem 3, so there needs to be a review of IR spectra. I think we're pretty strong on IR in particular. So we're not going to spend a ton of time on IR. But just to recap, NMR, proton NMR, so we can contrast that with carbon NMR. Carbon NMR is going to work a little bit different. So for proton NMR, the number of signals is the piece that's not on here, right? Number of signals tells you the number of protons. In carbon NMR, number of signals tell you the number of carbons. So the difference is that even a carbon that has no hydrogens attached to it, a quaternary carbon, will still show up in a carbon NMR because it's actually the carbon that allows this to work. But chemical shift works the same way. It's just going to be different ranges, but it's still going to tell you just about shielding. It's talking about the carbons being de-shielded. And it tends to be, anytime you can get a carbon-13 NMR, you can also get a proton NMR. So they tend to be used in conjunction with proton NMR, because why would you ever not have a proton NMR? If anything, that's the easiest kind to get. So if you can get a carbon NMR, you usually have both. So it's not going to be as exhaustive. We're not going to need to pour as much thought and effort into understanding carbon NMR as proton NMR, because we have more information usually. For proton NMR, we also have integration, right, which tells us relative amounts. That doesn't work for carbon NMR. Right, carbon NMR works. Remember that you can do NMR with anything that has a magnetic moment on the nucleus. But in order to have a magnetic moment on the nucleus, you have to have an odd number of nucleons. So for hydrogen, that's really easy because the default most common isotope of hydrogen has one proton and no neutrons, right? So basically, every hydrogen shows up properly. Carbon NMR, what's the default isotope of carbon on Earth? 12. Right? And so carbon 12 doesn't show up in a carbon NMR. So really, we're looking at carbon 13 NMR, which means only about 1% of carbons will actually show up in a carbon NMR. The nice thing about that is because we're dealing with, 10 to the 23rd of these molecules, that still means every carbon shows up in the signal, but it doesn't mean you can integrate, and it doesn't mean you'll see peak splitting, because the odds are you're only going to have one carbon 13 carbon in any given molecule at most. And so that means it can't interact with the carbons nearby to cause peak splitting. And it also means you can't rely on integration. So basically, carbon NMR is a lot simpler because there's no integration to worry about and there's no peak splitting to worry about. So all you really have is number of signals and chemical shift. It really is. I was going over these, making sure, because I've never done a ton of carbon 13 NMR myself, and I was rereading these slides, and man, it really is that simple. It gets tricky. Next quarter, we'll add 2-dimensional NMR. That gets really tricky because it's a lot more variables to keep in mind. So I'm just going to skip past the practice problems. But basically, the reason that we can take carbon 13 NMR pretty easily is if we have a Fourier transform NMR, which most modern NMR are, you can adjust the detector to look for a wider range of chemical shifts and response rates, which means basically by just changing a setting, instead of going from 0 to 15 and looking for the way protons interact with other protons in the magnetic field, we can look from 0 to 200 parts per million. And by changing the response rate, we're actually looking at carbons. And the reason that that's different is because carbon has a larger mass it's slower to flip backwards and forwards against the magnetic field. Remember that the whole idea behind NMR was that things with a magnetic moment. So if we had, you know, a spin of 1 up or a +1/2 upward, if we arrange a whole bunch of our strong magnetic field, the magnetic moment of that proton will point with that magnetic field. Same is true for carbon 13s, but because they're bigger, it takes more energy to flip them back and forth, and it happens slower. So all we have to do is adjust what the response time is and what the chemical or the hertz is, basically how long are we waiting and how much energy are we putting into it to flip it. And we can get carbon 13 NMR. But as mentioned, we can't integrate and we don't see peak splitting. So a carbon 13 NMR will just look something like this. You get a bunch of peaks. The number of peaks is really depends entirely on how many carbons you have. So the other thing is now oxygens won't show up. So we don't need to worry about the nitrogen protons or the oxygen protons because they're not going to show up in carbon 13 NMR at all. The other thing we do see is we do tend to see more noise that's harder to determine if it's an actual signal or not. So a lot of times, like sometimes it'll be really small, like these guys down here. If it's something that is impurity or solvent or some other issue, a lot of times you'll see it just labeled for you on the examples we're going to have for this class, because you don't have enough experience to be able to look at that and say, oh, that's probably this particular solvent we used. The exception being, just like with proton NMR, we're usually going to see a peak at 0. And that's the solvent that we're using to actually put our solution or our sample into solution. So tetramethylsilane will show up at 0, just like it did for proton NMR. All right, so with these in mind, if we're trying to look at this, if we have all sp3 carbons, and we're trying to determine where they're going to show up here, just like before, we're going to have sort of a standard range where we expect to find things. But just like before, methyls tend to be the most shielded, so closest to 0. And anything that's directly attached to an electronegative element is going to be more heat shielded, so further to the left. So we can look at that and say, okay, well, we can't integrate. We don't have peak splitting to tell the difference, but we can be pretty certain that this is going to be D all the way over here, because the most D-shielded carbon is going to be the one that's furthest to the left, directly attached to the oxygen. And then the methyl groups tend to be the furthest to the right. And if we're ranking these, the methyl group that's closer to the oxygen will be slightly more de-shielded than the methyl group that's an extra carbon away. So our most shielded peak is going to be this methyl here, followed by the methyl on the other side, and then our CH2 group is going to be this one right here. And so, and again, if we see this in conjunction with a proton NMR, they should match up pretty well. You'll have slightly different signals, but basically you can use this as a way to put the nail in the coffin when it comes to picking one of these versus the other. All right, so just to reiterate, no coupling, no integration. All we're really looking for is chemical shift, number of signals. So for carbon NMR, how many signals would we expect for all of these are dimethylbenzene, better known as xylene. If you've ever done any woodworking, xylene is really common paint, and a lot of times you'll see it sold in Nevada hardware stores as Xylol. I don't know why they name it that way, but XY. So these 3 xylenes, how many signals would we see? how many distinct carbons are we gonna have here?
Two.
One, two,
Two, and the rest of it.
3, 4. So this is because we're looking at the carbons and they're not gonna interfere with each other as much. We actually will see distinct peaks from the aromatic carbons now. Right, so we have 4 distinct carbons here. So we should see 4 peaks. If we were looking at the proton NMR of the same one, what would we expect to see? 1, nothing for those. And these would all kind of be lumped together in the aromatic region, right? Versus what would we see here? How many distinct peaks would we see here? So 1 for the methyl. Not, if we're talking about carbon, these are identical as well, so there's 2. 3,
5.
4, and 5, so we should see 5 signals here. And on this end, 1, 2, 3. Because this carbon is the same as that carbon. And these two are the same, and these two are the same. So carbon NMR is really, really valuable at figuring out what the substitution looks like on a benzene ring. Proton NMR is really good at telling you have a benzene ring, but it's not great at telling you where things are relative to each other on the benzene ring. Right, so carbon NMR is really good for that because just looking at the aromatic carbons, you're gonna get different number of signals depending on where things are substituted. Right, anytime your 2 substitutions are next to each other, you're gonna get a different pattern of peaks in the aromatic region than if they're one apart from each other or opposite from each other. All right, and so the handout I gave you has a textbook list here. The assignment file on Canvas also has the compound chemistry version of these figures as well, if you like looking at those better. And if you're trying to determine which of these is which, look at the chemical shifts. So on the left-hand side here, it goes from 0 to 10, and it's all the hydrogens highlighted that are in bold. So this is your typical shifts, chemical shifts for proton NMRs on the left, and your chemical shifts for carbon-13 NMR are on the right. So this gives you a fair bit of detail. It's a little convoluted. The even simpler version just looks like this. 0 to 50 is where you find sp3 carbons. 50 to 100 is either sp carbons or sp3 that are de-shielded by an electronegative element, so directly attached to an electronegative element. 100 to 150, sp2 hybridized, including alkenes. So your alkenes and your aromatics will show up in the same region with carbon-13. That's a little different. Because that was one of the things that's really, really nice about proton NMR is those aromatics make it really obvious. The only thing that shows up in 6.5 to 7.5 region really is aromatics. Here you can have alkenes showing up there. But again, if you have proton NMR along with the carbon-13 NMR, you can still tell the difference. And then last but not least, 150 to 220 is carbonyl carbons. They show up very specifically in that high range. There's not a whole lot else that will show up there. And you can tell with a little bit more certainty the difference between a primary carbonyl versus an acid carbonyl and an ester carbonyl show up in that 160 to 180 range, versus ketones and aldehydes show up even further and closer to 200 to 220. So remember from IR, we couldn't really tell the difference between all of our carbonyls. We could tell we had a carbonyl, but we couldn't really tell anything beyond that. This gives us a little bit more. We can tell an aldehyde and a ketone apart from carboxylic acid or an ester. If we're looking for, if we're trying to predict what the NMR spectrum would look like, for this one, first off, how many signals would we expect for this? How many distinct carbons do we have, not hydrogens? 1, 2, these are the same, so that's 3. These are the same, so 4, 5, 6, 7. So we should have 7 peaks. These ones are going to be in that 0 to 50 range. This one will be in that 50 to 100 range because it's sp3 carbon, but it's de-shielded by the oxygen. And then all of our aromatic carbons, we should have 4 signals in that 100 to 150 range. Right? Because, and that one should be the most de-shielded of those. So most de-shielded second, and then, so going from left to right, 1, 2, 3, 4, all in that 150 to 100 range. And nothing above 150, no carbonyls here. We have the oxygen, but the oxygen is not a carbonyl. Right, so again, this is a really simplified way of looking at it. It's not a bad way to, at your first stab at trying to interpret it. Start from this, and then when you need to get more specific, pull this out.
This was more helpful than this.
It is once you know what you're looking for, you'll come back to this more often once you get these categories down by memory. Because especially the being able to tell the difference between the carbonyls and things like that.
Oh, thank you.
And I'll make sure, so I'll put this recording, attach this recording to the assignment file, and I'll put it in our week overview as well as these slides. All right, so here's an example. We got formula C9H10O2. And we figure out the structure just from the formula of the carbon NMR.
So.
Yeah, C9H10 means
Seems like there's a benzene ring.
seems like a benzene ring. And that means we should see a bunch of peaks between 100 to 150, which we do. 1, 2, 3, 4 peaks. So that means that all of our carbons are chemically distinct from each other on our benzene ring. Which the most common way that you see that is if we have 2 things attached on opposite sides and they're not symmetric. If we had 2 things attached on opposite sides and they were symmetric, we would only see 2 different carbon peaks in that aromatic region, right? The fact that we see 4 tells us they're probably opposite each other and they're different. Because what if we do, this is X and this is Y? Now, we should have 1, 2, 3, 4, 5 peaks. Actually, not 4 or 5. They should be all chemically distinct from each other. Should get 6 peaks if they're in this position and asymmetric. And if they're adjacent to each other and asymmetric, same thing.
Yeah.
Right, so the fact we have 4 tells us the substitution has to look like this.
Then we got
double bond to an oxygen. Right
We
there.
got something showing up in the carbonyl region. Only one peak in the carbonyl region, but we have two oxygens. So what does that tell us?
Carboxylic acid.
Could be a carboxylic acid, could be an ester. And so, but then we only have two carbons down here. So 6 of our carbons. We have 6 carbons in the benzene ring out of our 9 total. And then 3 chemically distinct ones here, so this being all the way down here, one of these is probably a methyl group. And now we have 2 carbons left to go, right? And it's an sp3 carbon directly attached to, yeah. Actually, what if it was mono substituted? How many, that would give us 4 carbons too, right? We get 1, 2, 3, 4.
What about the methyl?
So that we could have an ester. So we have a couple of options. We have this, that would work with what we have here, right? Except that what's in that, this one's in that 60 range, which is either which is an sp2 directly attached to an oxygen. So that tells, that's a clue that maybe we have ester. Right, because here we don't have anything, any sp3 carbons directly attached to an oxygen. So the fact that this peak is 60 tells us that maybe what we have is that. Or potentially put the carbonyl right here in the CH2. And so we still have a couple of possible options. But once we know what we're doing, this is narrowed it down a lot more than we would be able to do with just an IR in a formula, or even just a proton NMR in a formula, right? Especially considering it gave us the substitution. It's either mono substituted or di-substituted with them opposite from each other. That limits us a lot right there. And this would be the case where it would be a quick IR would allow us to tell the difference between those really easily too, right? Because carboxylic acid is super distinct on an IR. Think probably. So the fact that all of these are relatively close to the same, I think. And it's probably. This one. Mainly just because this methyl peak being all the way, pretty close to 0 tells me it's pretty shielded. Putting this carbon right next to the oxygen. If we put the methyl directly next to the oxygen. And the CH2 on the other side of it, that wouldn't make as much sense, because then we should have 2 that are pretty de-shielded as opposed to 1 that's pretty
Could we
de-shielded.
just add another methyl group to the top, and then that would limit the amount of signatures we have here? To the LA and stuff about it. Never mind.
That's still a possibility.
I don't know how we're counting these, messy signatures, are we just counting that as one or?
So that, if we zoom in on it. And remember, we're not looking at peak splitting. So that is 1, 2, 3, 4
Got it.
signals there. That's how we do it. It's either opposite here, or it's going to be a monosubstitute. And that's again, something that a proton NMR would allow us to distinguish between that really easily too, because your aromatic region is either gonna have an integration of 4 or 5.
Right.
Right, so in the absence of everything else, we still have a couple of options. We can be pretty sure it's an ester. And we can be pretty sure that it's either, and we know it's either monosubstituted or opposite substituted there. And then if we had a little bit more information, that would be enough to really finalize it.
What's on the reference sheet or postal 120, there's a benzene ring, but slash one of the double bonds and a Y.
That's just saying, if you have anything, a substituted benzene ring.
Oh, okay.
It's just the Y is just connecting to the middle of the benzene ring, saying if it's anywhere in there. If anything is attached to a benzene ring, that's where the carbons will show up.
Awesome.
All right. So one last bit. To make things complicated. We can actually process the signal. To actually finalize it, so we can actually get it, it's not quite the same as integrating. Because integrating told us how many hydrogens were in the signal in a proton NMR, right? But this can tell us the number of hydrogens that are attached to a carbon. Because the carbon 13 is gonna have a certain interaction with the protons attached to it. So if we process the signal just right, and they call this DEPT, which stands for distortionless enhancement by polarization transfer. Basically, we can take that same signals. So broadband decoupled is just what we've been looking at. All of our peaks look the same. Basically, DEPT and changing the signal will either make some of them disappear. Basically by canceling them out. Or make some of them negative. Depending on the 90 versus the 135, and it has to do with the degree of polarization. You notice that those are numbers that are related to angles, right? So 90-degree polarization versus 135-degree polarization. And what that means, so this is what we normally look at. If we then look at the DEP 90, anything that's not a CH where you have more than or less than 1 hydrogen will disappear. And then if you look at the DEPT 135, odd numbers of protons will be positive, even number of protons will be negative. And no protons disappears. And again, you never are going to see just the DEPT 90. You'll usually see this in conjunction with the standard decoupled. So what that looks like, I put that cheat sheet off to the side here. So if our broadband decoupled looks like this, and the DEP 90 looks like this, that tells you that right off the bat, you've got a CH carbon, a carbon that has a single hydrogen attached to it. Because one of your signals stayed there and the other ones all disappeared. So that actually right there is enough to answer what's the structure of C4H10O. If it's an alcohol,
Yeah.
we only have 2 options really, right? It's either 1 butanol or 2 butanol. Which is it based on this?
2-butanol.
It's gotta be 2-butanol, because if you draw out all of your hydrogens.
It needs to be a tertiary carbon.
It's not quite, it's still a secondary carbon, but it's a carbon that has the alcohol attached to it, only has one hydrogen attached to it as well. Right, so. We should see. We should see. 4 signals here, I think I cut this off. How did I do that? I guess we do have more than one option though. Because we could have a methyl group as well. Right, so because otherwise this should give us 4 signals, we don't see 4 signals here, right? So it can't be this one, but it could be.
It would have to be not known carbon.
If we put it there, we don't have a single CH, right?
No.
But if we put it here. Now we've got 4, we have 1, 2, 3 distinct carbons. One of them is a CH.
Don't need CH2 as well though.
And then that we should have, that's a CH2, so we should only have 1 CH2 as well. Which is what we see here, and it's the one most de-shielded, the one that's directly attached to the oxygen, which all makes sense, right? So again, just like we've been practicing, start with everything that's a possibility for the formula and the easy stuff to see. And then start ruling stuff out because of the additional information. You don't need to look at both of these right off the bat. In this case, this is a small enough molecule, we can draw all the possible options pretty easily. And then just start crossing stuff off. There's no one silver bullet for these. But there's enough that you should be able to eliminate everything except for one option. All right, so I think one of the examples, all the problems in here. So the first page gives you an IR, a proton NMR with the integration. And a carbon NMR with some extra detail on it. Second example, same thing, gives you IR and formula, proton NMR, carbon NMR. It's a little bit messier of a proton NMR, lots of splitting, lots of signals, but we should have enough information to do this. And then I think he doesn't get to, so the first 3 are all pretty similar, just practice with each of them.
Mm-hmm.
The last one gives you DEPT 135, as well as the decoupled. So on the back page is the only time you need to use this. The rest of them you're able to figure out without. Right, so my advice, don't try to make the carbon NMR do too much, it's just one extra tool. You still lean more heavily on the stuff that was practiced more. But they should all be able to agree together. Right, if you eliminate all the one option using the proton NMR, but that proton NMR doesn't agree with your carbon NMR results, then maybe you missed something. Or you scratched out something that you're not supposed to. If you eliminate all the possible options, then you did something wrong, right? Because there is an answer to each of these. It's processed to make the signals look cleaner, but this is real world data. So you should be able to get real answers for these.
For the first page, it says there are 2 unresolved lines at 130 ppm. Does that just mean there's 2 lines right there? So
Yes, that means it's 2 signals.
6 altogether.
6 signals altogether. And in that region, that probably means that's 2 aromatic carbons that are close to the same, but aren't technically identical.
Mhm.
Right, and then you do also frequently see things like this, where you get a peak that's much smaller than the rest. That usually that's leftover solvent that you didn't fully dry out your sample before you took your NMR of it. You get a solvent impurity in there. The nice thing about that is if you're using standard solvents, you just look up you look up where your solvent would show up in a carbon-13 NMR and be like, okay, well, I can cross those off because I know that's just the acetone or whatever.
Like for the first one, all the way up around 160, this sort of magnitude, would that probably be?
It's not labeled as being solvent.
Okay.
So I assume that that's an actual signal.
And there's oxygen in this molecule, so there has to be a peak between 40 and 160.
So a peak between 140 and 160. Yeah, so it might not be a carbonyl. It might be an aromatic carbon. Especially an aromatic carbon attached to an oxygen, potentially. All right, so I'm gonna leave you to work on these and take your melting points from last week's lab. Mariola's around, but I need to go pick up stuff at the pharmacy. But we can go over these and we can talk about these and work through some of them too in lecture on Thursday. Like I said, it's just practice with synthesis. You can also be working on some of these as well, since I have to bail right now.
And is this stuff gonna be on the midterm?
It will not be